Again, I do need to kind of turn up the rate a little bit. I did make so we were talking about position and momentum. We're going to get to momentum today. Last time, I did make a mistake. I don't know how much of a mistake I made. Hopefully, and I guess I could watch the video, but again, yeah, I had a grand do. If you're going to translate a wave function by some delta amount, well, no, let me do it this way. Delta prime. Remember, the little prime is a placeholder. Okay, I think I wrote a plus, and then everywhere else I use minus. It's minus. Sorry about that. I have it in my notes as a plus. I remember in class getting a little flummoxed about what was I doing. So it's minus. I looked in your book, it's minus, and all my notes is minus except for when I introduced it. Now recall that the purpose of this thing, this is weird, although it's going to give us a lot of neat stuff. Okay, here's a state. Here's a wave function, which we now know is, let's call it this. What this thing does is says, okay, if you know what the wave function there is, this thing tells you the wave function a little bit left or a little bit right. And as I was telling you, I know I shouldn't like spend a whole lecture and then say, oh, this is useless. Don't worry about this. Why am I doing that? Why am I talking about it then? So this tells you the wave function a little bit left, a little bit right. So I already have the wave function, so I don't need that. All right, so it really is kind of dumb. However, remember that this is also how you're going to translate things. This is how you're going to rotate things. It's how you're going to translate things not in space but time. So this is a good warm-up. You're going to see this again and again. The next thing, what we're doing today is we're going to figure out not so much about position. We all understand position quite well, especially now that you've seen this a zillion times. So that's the Dirac representation of wave functions as you've known them. But now we're going to work in momentum. And remember, I told you, and I can even do this. I know enough, and you'll be able to do this really by next lecture. You know what I've drawn here? This is the momentum. That's the momentum representation of the same wave function. Again, you'll learn how to do this by the end of next lecture. Same, because I drew a bell shape, it's also a bell shape but narrower. And the center would be zero. Okay, blah, blah, blah. So you're going to figure out how to do that. And it's just kind of cool. And as I mentioned to you, momentum, nature sees momentum no differently than nature sees position. These are the same thing to nature. If you do solid state electronic structure, again, I think that's a bunch of you, you cannot think of position as of wave functions, because in a solid state material, the wave function exists over the entire chunk of whatever you're studying, and you can't visualize it. So I was just talking about visualization. How do you visualize that? How do you visualize 10 to the 20 atoms, right? You can't. So everything has to be done in momentum. You have to think in terms of momentum wave functions when you do solid state electronic structure. Again, I'm pretty sure there's a bunch of them. Okay, so we talked a lot about this. Sorry about that. Okay, now I also mentioned that the only operator here, this is just a bunch of constants, is k. And I think I already told you k will be momentum, but now we're going to prove it. So k is the momentum operator. Let me walk you through how this is done in the book. I thought about skipping this, but so let me try to do it real quick, because this proof and the next proof are, God, these are really mind-bending. They're not that far. They're not that bad. I don't know. It's weird in a unique way. And in fact, number 1 or 2, I had you do the uncertainty principle with Dirac notation. And I've shown you how to do that. It's even in my little textbook, how to do the uncertainty principle with momentum and position using just wave functions. But when you do it with Dirac notation, all of a sudden you're like, wait, this shouldn't be that hard, and you're just going to get cross-eyed. So I wanted to do this because it's actually really similar to what you're doing on your homework, using Dirac notation to do the uncertainty principle. Again, it's just really awkward. Okay, now it starts out not too bad. Remember, these dashes are just placeholders. And now I'm just simply changing the order of the operators. And this will not be 0. Okay, then what we're going to do is let's apply a ket. So, like on your homework, you're actually looking at the commutator of x and p, but you're going to do the inner product, right? So you got a ket and a bra that bracket it. That's going to make it real. You know, that's how you get that final value of IH. Okay, so what have I got? Okay, so let me do this one first, and then I'll subtract this one. This is a bit involved. So just make sure that you don't lose track of the fact that I'm just doing the first term first. It's just that this is going to, this takes a lot of space up here. Okay, so there's a translation operator operating on the state, and then what you get is sorry. Okay, then the position operator operates on the state. There we go. Okay, so not too bad. Now let's subtract from that. So this is the next spot. And we can state x. X prime, sorry. I got a little bit, again, placeholders. They don't, none of this stuff does not mean anything. Let's see, what have I done? Oh, okay. So I'm going to just remind you that that minus is because we're subtracting this from the first term. It's not there on its own. Okay, the position operator, of course, returns the eigenvalue, which we talked about last time. And then what you then do is you can, oh, I don't remember that one. You can actually now hop this over here. And what you're going to end up with is on this x prime. Of course, the translation operator then moves the state over. Okay, now notice that my operation is to subtract these two. And so you notice that what you get is okay, so there you go. So there's a residual that obviously implies that there's an uncertainty principle here. Now, here's something that kind of bothers me. We have to set up an approximation. And here's the approximation. Now, it's not, I mean, remember that partials are 0, right? What we're going to say is that it's not really moved over. That's for the next step. This is step 1. Again, the goal here, by the way, is to figure out what the K operator is and its momentum. Okay, now the thing that bothers me about this is that we're doing all this crazy exact derivation. We're trying to be perfect in our mathematics, just like you don't just assume that the sum of x to the n over n factorial is the exponential. You have to prove it using some highfalutin theorem. Here you make an approximation, and it's essential to do it. So it's like, why am I doing this to begin with? Anyway, sorry, this is how it is. Okay, next one. Okay, now we're going to do this. And what we're going to do is we are going to, notice that I'm basically, notice that I'm redoing the evaluation. I've got I'm going to bracket it in position. And what I'm going to do now is, it's kind of like, well, wait, have we already done this, right? So, I mean, if you look here, if I bracket this is just a number, right? It's technically an infinitely small number. Okay, now, so this is the same thing, except I'm going to do it differently by not just having the operator move a ket. I'm going to actually insert this jazz here. So I'm going to, so this is how K gets incorporated. You don't see K in here. Again, the translation operator simply moves kets. Here I'm not going to actually do that. I'm going to represent the translation operator and just see what happens. Okay. Now hopefully I am not going to lose my mind here. Let's see. Okay. Okay. So X T. Yeah. I'm actually rewriting it. I shouldn't do that, but I'll do it anyway, just so you don't get lost in your notes, or I don't get lost. Okay, now let's, what does that do? Okay, now I'm going to insert that stuff. X is X. The translation operator is 1, so I'm just multiplying through. X, K, so now we've inserted K. Okay, now I'm going to subtract. Okay. Notice that I permuted the order of K and X. So there you go. Hopefully I haven't screwed that up. Okay, now, one of the reasons I was terrified of today is because I have to use the board perfectly. See why? So I'm blending the two. This is an example of doing one proof, stopping, then doing another proof, and adding them together. I hate these, but what are you going to do, right? Oh, God, look at this. That's this kind of stuff I shouldn't say, right? Okay. Next trick. Now again, I want to point out that this comes from our first proof. You don't have anything that will tell you that all this is that. Okay, next trick. Next trick is divide by looks like I don't know that I needed these. I don't think I needed these actually. So I'll stick with them. I just realized I don't actually have them in my notes. I just decided to do them. Okay. Well, here. Okay, so I simplified things a little bit. I x k over. So notice I've got minus xk plus I dx minus kx over I dx. I need separate brackets. That would look perfect. Okay. Okay, if I divide all of that by let's see, that would be 1 over I minus I. Okay. Okay, so then what you get to is, can you guys see this? xk minus kx Okay. So there you go. Now you got the commutator. And so there, yeah, sorry if you folks don't mind it. I'm just kind of terrified. No, minus, plus. Sorry about that. Sorry about that. Minus, right? So now what I can do is multiply through by minus, and so I'm going to do that by. So notice that I multiplied. I multiply here by a minus sign, so that's kx minus, so xk minus kx, which is that. Okay. Wait, no, I need to. I want to do this exactly right. Now on your homework, what you show is this. You actually need some of the lessons that we're covering right now, and what you then do is combine to show that K is momentum over each part. So that's the argument. I know this is such a pain. But it is, if you can, kind of follow along, then you'll be okay when you actually do this problem on your homework using Dirac Notation, using two resolutions of the identity. And I'll show you how to do that part in a minute. But just anyway, so you get the flow of this stuff. I want to point out that, again, for doing this insanely accurate, perfectly perfect proof, there's an approximation made which kind of blows the whole thing, or kind of blows up the whole purpose of doing it. But anyway, there you go. That's how you prove that in the language of quantum, the language of the book, momentum is the driver of translation. And the reason that's significant is it actually is connected to classical mechanics. Momentum moves things. Of course it does. Momentum is just another word for velocity, right? Velocity times mass and momentum. When things are moving, then things have velocity, they move. Now, you think like, well, of course, but now remember that quantum and classical Isaac Newton stuff, they usually are not connected at all. I mean, this stuff is really the antithesis of Isaac Newton. And let me point out, to give you an example, all right, velocity, mass times velocity is momentum. Velocity is the change in position with respect to time, right? Velocity is the change in a position of an object with respect to time. So there's your momentum. But a momentum operator is the change in something that represents position with respect to position. Whoa, they kind of look the same. It's a derivative. But time and position, those are pretty different. So anyway, I just want to point out that that you have anything that's kind of looking classically is kind of shocking when you're in the world of quantum mechanics. Okay, so all right, the next bit is if you want to move something a lot, what you would do is get the translation operator that is really moving. You need to move over a very small step and then raise it to the nth power and let n go to infinity. Again, it's another mathematical conundrum. Mathematicians get so worried. What happens when you raise a partial to the infinite power, right? Partials are infinitely small, but the infinite power is also infinitely large, and the two have to fight it out. And you have things like the L'Hopital's rule to figure. Anyway, mathematicians get so, concerned about these things. And then at the same time, you run into these hand-wavy things. And what is that? this would be, okay, so this would be the limit. So it gets a little bit more complicated. We'll see why here in a second. Why am I writing a limit? So it's minus I, P over H bar. Okay, now my delta X will be the macroscopic, move it like a nanometer over n. So there's dx, right? And that's, oh, no, curly bracket. I can do curly brackets. There you go. Okay, and it turns out that this is a big surprise. And now you are hopefully seeing more about why are we always doing e to an operator, right? P operator. E to an operator. Keeps coming up over and over and over again. That's my point. E to an operator. There's so many things work this way that, because the next thing we do actually right after this Friday is time. And that will be time, the change in time, and that will be the Hamiltonian, by the way. That's where we're going. Notice that it has the form of a unitary operator. If I just had an operator here, then I had the transpose. Sorry, I guess I supposed that. Anyway, so it looks like your little rotation unitary operator already. So there you go. Now I also want to point out, I don't want to spend too much time on this, but your book, I'll put this in the next problem set. Your book goes off on this. It's kind of a high level understanding of, the book is really concerned with this. I'm not so concerned with this, but I just want you to know because in case, God forbid you read it, okay? When it comes to commutators of position, obviously that would be, now I and J equals X, Y, and Z, right? So we're going to use X for any dimension. So I'll just say, so really I should say like X and X, or X and Y, X and Z, and it doesn't matter. There's no reason to say that what's happening in one dimension affects another. That's the plain spoken way to do this. The same for momentum. Momentum in X really should not be affecting the momentum in Y. Of course, if you are talking about momentum in the X direction, do you know the momentum in the X direction? Of course you do. Of course you do. That's just said you knew what it was. And of course, then this guy is our uncertainty principle, and of course that's equal to IH bar. But it does need to be said that it needs to be in the same direction. If you want to know where something is in this direction, and you want to know how fast it's moving in this direction, you can't. But if you want to know where something is in this direction and where it's moving in that direction, that would be okay. Unless you're asking about that direction, now you screwed up again. So details, this doesn't come up again. Now the thing I'm going to put on your book, the thing for your book, I'm going to put it on your homework, and I won't say too much about it, that these are related to what are called Poisson brackets. So your book brings it up all the time, Poisson brackets. And I'll put it on the homework and show you what they are, because I don't want you to not know, what the heck are they talking? Why are they always bringing up Poisson brackets? It's actually a classical thing, Newton's equation of motion. So you know that you can just take velocity times time and figure out where the new position is for your object. And you learned that in physics high school, right? It turns out that when you have to solve really complicated things, like the motion of a pendulum while attached to another pendulum, something like insane, the physics majors, like their senior year, they learn about Hamilton. You get this? You heard this term before? Hamilton's equation of motion. Hamilton, same guy, Hamiltonian Hamilton. So Hamilton figured out, whoever he was, that geezer, he figured out a whole other way to describe where something is in the presence of forces and gradients and potential and going downhill while you're on a pendulum and all that jazz. He figured out a mathematical way of solving really complicated types of systems. That's not terribly difficult, but part of the mathematics of Hamilton's equation of motion are Poisson brackets. They're an integral part. And what it turns out is that Hamilton's expression of Poisson brackets and quantum mechanical equations of motion, but by like the stuff we're doing here, they're really similar. They just don't have, Hamilton stuff doesn't have I or H bar in it. So it's like take Hamilton's equation of motion and put an IH bar in front of all of his equations, and then you get the quantum mechanical things. So that's kind of cool. A lot of people thought that was really fascinating that it works that way, but I don't really get much out of it aside from that. So I'm not going to say too much about it, but that's what it is. I can link, if you really, really want to know more about it, there's this guy at Stanford, a physicist, who he does what I do. He does what I do. He puts his lectures online, and he talks about Hamilton's equations of motion and Poisson brackets. And he is like really entertaining to watch. And so if you're interested, I'll post that. Anyway, all right. So the next thing we got to do is it's kind of fascinating. The book actually wants to describe what the momentum operator is. The reason I want to cover this is because the momentum operator, for it to function properly in Dirac notation, it has a really strange property. The momentum operator behaves very, very strangely in Dirac world than any other operator. And so you need to know about it to do your homework. Okay, now what kind of pisses me off a bit is that we've done this to death. Okay, I was just talking about it, right? And you know, that's p squared over 2m. And so, therefore, you can just say momentum is just the square root of minus, right? Sorry, double derivative. I didn't mean double derivative, right? So you just say momentum is that. There's no 2m, right? 2m. So then you get minus IH bar dx, which is correct. So this seems to me to be a pretty good proof. But that's not how we do it. That's not how we do it in Dirac notation. Okay, so and look, don't even write this down. It's not important. Right? I mean, you already know what the momentum operator is. You've seen it 1,000 times. Okay, but Sakurai has an overwhelming need to prove it. And as I warned you that there was going to be there were two hideous derivations. This is the second one. We'll largely be done with this. Okay, let us translate. What am I doing? I'm going to translate a state. Okay, I'm going to translate a state by placeholder. So 1 minus p over h bar. I'm going to have several resolutions of the identity. I mentioned to you that I wanted to do this to make sure that you're okay with how to do resolutions of the identity as it applies to the translation operator. Okay, so what I'm doing here is I just applied the translation operator to the state. Now what I'm going to do is I am going to leave the translation operator as it is, and I am going to represent the state in its wave function form. So there's a resolution of the identity, and there should be 2 dashes, right? Now, all right, okay, remember this goes with that. That's why there's no dash. That has a double dash. And hint, because I'm going to resolve another identity in a little bit, and that will be a single dash. These are all positions. It's just convenient placeholders. If you plan really well ahead of time, you can get these dashes just right. So to hopefully be as minimally confusing as possible. And you can see why I'm going to need to resolve an identity, because that by itself, hopefully as you see more and more, I'm gonna have to do something with that. Here as well, heads by themselves don't ultimately answer any questions. Okay, and then what I'm going to do is I'm going to translate the ket. Okay, so not too bad, right? Okay, as I warned, let's go ahead and do something with this. Now again, you see that I have had to be quite careful with my space here. So I'm not doing anything with this yet. Oh, double dash, double dash. I'm going to have my single dash here at some point. Okay, now this is, again, one of those steps that I find kind of angering. X minus. Okay, don't get too cross-eyed. Oh, bothers me. The bracket should line up nice. There we go. It will look a little nicer. Okay. Don't not pay attention to this. Okay, notice what I did. Okay. Now, again, unfortunately, these proofs all have little half-assed things. Oh, we're going to make this proof exactly perfect, and then we're going to do little half-assed things when it's okay. There's no big complicated things out there. So the idea is that position is relative. So this is saying, yeah, this is just a translation operator. It's like, okay, you know where the wave function is. So here's what it looks like a little bit to the right. But that's no different than if you knew the wave function. I've already got confused. Okay. So here's where you're at, and that's where you're going. And this is if what the hell is that? That's to the right. So now that's to the left. Okay. Yeah. You see. So that's like. Okay. I get it. All right. So this is like what this does. It says you're here, so I'm going to tell you what's there. Then what this does is it says, all right, let's say you're to the left, then I'm still telling you where you are to the right. But since position is arbitrary, I never really said what position I was at. It's no different than, I could just say, well, I was starting out in the middle to begin with. Look, it's a little half-assed, okay? I hope you follow along. This is here. This is here, but then since position is arbitrary, I just rotated it back to there. Whatever. I hope that's not too angering. Okay, so that's what that is. Okay, and then there's going to be one more thing that's going to make you angry. Okay, I'm going to rewrite this. I'm not doing anything with this yet. So I'm just rewriting it, which sucks. Why maybe I should PowerPoint. But I like to do this because I hope we can kind of keep pace with each other. Okay, now I'm going to do one more thing, and I'll explain this. After I'm done, because this probably appears to come from nowhere. And the book does not explain this at all, at least my version. I don't know what you may have found on the internet, i.e. Blackboard. Better delete that and post it. Okay. All right. Just so you know, this is turning into that. Now again, the book doesn't explain this, but it's actually an incredibly easy thing to understand. I'll explain it in a minute. It's actually this. way. It'll make more sense in a minute, but let me just finish up. Okay, God knows. Now what am I doing? Okay, so. Okay, so now what I'm going to do is all of this is under the purview of this integral. So let me make that a little bit more obvious. Rewrite this again. You may notice that that first part on the right is actually this first thing on the left. So those are going to be canceled. Okay, so now it'll be a little bit more obvious. Yeah. Okay, integral dx. X. I'm just undoing the bracket. Okay, notice here and here. And don't forget, if you're like, oh, that means I have twice that. No. When they're the same sign across and equal, then they're going to cancel. Sometimes I mess that up myself. Okay, then now I still got an integral minus all this jazz. Dx. X. Oh, okay, from here, right, so this is, that's where that's coming from. Oh, yeah, there we go. That part. Okay. We just thought that some new terms appeared out of nowhere. Oh, there we go. I don't need any more brackets. Okay, so now what you see is, told you this sucks. These minus signs will go away in a second. Is equal to minus the integral x. I'm writing the same thing over again. Notice that I'm going to have to do some things you're going to hate me for doing this, but this partial is a number, so let's get rid of that. Let's make them positive. Okay, so now what you end up with, and yeah, one time. So okay, so now I've got I P alpha over h bar equal to x. Okay. Let's see here. What do I want to do? All right. What I'm going to do now is I'm going to do this, and there's my single dash. Oh, that sucks. Good job. There we go. I'm also going to bring over the constants. Okay, so notice now I've got the operator defined. So this is really what I'm trying to get to. And now I've got, maybe that. Notice that I just created a delta function. So that means that I wipe out my integral. And I'll wipe out, what am I going to do? I am going to wipe out x and x prime. So now, God, this is really awful, isn't it? Is equal to h bar. Or as I often actually know it, I usually, you see me always do each bar over I. In fact, I did that a little while ago, I believe, same thing. Okay, now, painful as this was, let me point out what it does is, it shows you that when you got momentum, its job, again, this is bizarre, it jumps out of the inner product. See that? It jumps out of it and lets this part collapse on itself. That's bizarre. So you still see that, you still see the momentum operator just as you've known it, but it does this extra weird thing. Also, so if alpha, let's make this x double prime. Now I didn't say what alpha was, right? Now this you need on your homework. So what you do on your homework is resolve identities on the proving the uncertainty principle. Resolve the identities between the x and p operator to make sure that you get p to look like this. And the reason is that you get x. The reason is that then you kill off, as soon as you resolve an identity which introduces a integral, it automatically kills off the integral at the same time because we did it with the delta function. Last bit, let me give you just another example of how to use this. Let me actually go backward with that. Instead of making alpha a state, let's say that you have this field. If for some reason you have to solve this, what you do is you resolve an identity. So again, this is very similar to what you do with your homework. And again, I'm going to put that in front of P. And then that leaves alpha. Okay, then resolve an identity again. So again, you can see why, because as soon as I do that, there you go. And then this thing ends up being h bar over I. So it ends up being a integral killing the Dirac delta function, and the end result ends up looking basically like this. We got a wave function, the beta wave function is a function of x. So you may recall very early in the class we actually learned stuff like this. There you go. So again, Dirac, which up until now has made things easier. Until you get to this, then it gets harder. So sorry. Turns back into what we had covered before, right? So this is an expectation value, right? It has the same form, and it returns back into wave function star operator wave function. Maybe beta and alpha are the same state. They probably will be. Anyway, there you go. So, and of course, this is going to help you on that the uncertainty principle calculation, which, as I mentioned, is really kind of a biz knocker. But you've seen me. It's weird. It's not hard. It's weird, and weird is a type of hard. So anyway.